In the last video, I showed you the qualitative explanation of single slit diffraction. We avoided the mathematical explanation in the previous video. Today I will show you how to do the mathematical analysis of the intensity distribution through single slit diffraction. So if you can remember, we did a single slit as shown here. This is a single slit, and consider the light source is at infinite distance, so that the light rays rendering parallel to each other will pass through this single slit. And here you have taken the screen, the point of observation P. This is the point of observation P, and here we need to find out what will be the intensity, maximum, minimum, secondary maximum and all. So here we said, let us draw two straight lines AP and BP. So the path difference here we have already derived. If the slit width is A and the angle of diffraction is say theta, then we said this is A sine theta. Now this A sine theta, the path difference between AP and BP, will decide what will be the intensity at the point P. So now, as you have already done, let's say this single slit AB, on this wavefront you have many sources, many secondary sources which will contribute at the point of observation P, which will contribute to the intensity of the intensity at the point P. So now here, if I will consider the path difference from A to P and B to P is A sine theta. This is A sine theta. So path difference is A sine theta, so I can write, so the path difference is equal to A sine theta, where theta is the angle of diffraction. So the phase difference will be, phase difference can be written as 2 pi upon lambda into A sine theta, the path difference. So let's take this as beta, or let's take this as the phase difference between AP and BP, the light rays moving from A to P and B to P. So there are n number of such sources, secondary sources here. So the consecutive phase difference, the phase difference between the consecutive secondary sources can be written as, we can write this phase difference between consecutive sources, secondary sources, can be written as, if n number of sources are there, then 1 by n times 2 pi upon lambda A sine theta. So let's take this as beta. So beta is the phase difference between two consecutive secondary sources. So now if I will write n number of such sources are there, and I will write the wave equation for them, then for the first one, let me write y1 equals to A sine omega t, where A is the amplitude, and if I will consider identical sources, secondary sources, the amplitude of individual source will always be same, which is A. So y1 is A sine omega t, y2 equals to, similarly I can write sine omega t plus, we said the phase difference between two consecutive secondary sources is beta, so omega t plus beta, and y3 I can write the same way, sine omega t plus 2 beta. So for the nth source we can write yn equals to A sine omega t plus n minus 1 times beta. So this is for the nth source. So to find out the intensity, to find out the resultant displacement at the point P, from which you will be able to find out the amplitude as well as the intensity, we can take the linear combination of all these sources, y1, y2, y3 and yn, and write the final resultant, the resultant wave. The resultant amplitude can be analyzed further to find out the intensity distribution at the point P. So if I write this as y1 is A sine omega t, to make it mathematically simpler, we can take the complex representation of the oscillatory function. So I can write this as imaginary part of a e to the power I omega t e to the power I theta form, which is cos theta plus I sin theta. So if I consider the imaginary part, it can be written in the form of a sine. So imaginary part of a e to the power I omega t. Similarly, I can write y2 is the imaginary part of a e to the power I omega t plus beta. Y3 also imaginary part of a e to the power I omega t plus 2 beta. Similarly, for nth term, we can write this is the imaginary part of a e to the power I omega t plus n minus 1 times beta. So this way we can write. So to find out the resultant displacement y, we can take the linear combination of all these y1, y2 plus up to yn. So I will combine these terms and finally write the resultant term, and we'll take the imaginary part of that final term that we will get. So if I will now add this to find the resultant displacement y, which is the linear combination of all these n number of waves, we can write y equals to now a to the power I omega t plus a to the power I omega t plus beta plus a to the power I omega t plus 2 beta plus up to the nth term is a to the power I omega t plus n minus 1 times beta. So taking this a to the power I omega t common, we can write this as 1 plus a to the power I beta plus, e to the power I beta only, e to the power I beta plus e to the power I 2 beta plus up to plus e to the power I n minus 1 times beta. So this way we can write, so this is in the form of 1 plus r square up to this. So we can write this as a to the power I omega t 1 minus r to the power n, which is e to the power I n beta, divided by 1 minus r, which is I beta. So this can be written as a to the power I omega t, taking this e to the power I n beta by 2 common, we can write this as e to the power minus I n beta by 2, and this is minus e to the power plus I n beta by 2 divided by, similarly here if I will take e to the power I beta by 2, then this will give us e to the power minus I beta by 2 minus e to the power I beta plus I beta by 2. So if I will take a minus common, then we can write this as e to the power I n beta by 2 minus e to the power minus I n beta by 2, which will be in the form of e to the power plus I theta minus e to the power minus I theta, which will be 2I sin theta form. So that way we can write. So finally I'll be able to write this as e to the power I omega t, and from here we can write e to the power I, this is n minus 1 times beta by 2. So I omega t, and here we got e to the power I, this is n minus 1 by 2 times beta, and here we got 2I sin n beta by 2 divided by 2I sin beta by 2. So 2I got cancelled. So final term we can write as y is equal to a to the power I omega t plus n minus 1 by 2 times beta, then this sine n beta by 2 divided by sine beta by 2. So here this is the oscillatory function. So imaginary part of this we will consider, and the rest is your amplitude, that is a times this gives you the resultant amplitude. So if I write this, if I will consider the imaginary part of this result that we got, we can write this as r times sine omega t plus n minus 1 by 2 times beta. So this is the oscillatory function, and this r stands for a sine n beta by 2 divided by sine beta by 2. Sine beta by 2. This beta is the consecutive phase difference between two consecutive secondary sources that we have already calculated. Beta is equal to 1 by n number of sources, so 1 by n multiplied with 2 pi by lambda of a sine theta. This is what we have taken this beta as. Okay, so analyzing this resultant amplitude r equals to this will give us the intensity at any point on the screen. Okay, so if I will take this n beta by 2 as alpha, if I take n beta by 2 as alpha, then we can write this as r equals to a times sine alpha divided by this beta by 2 will be alpha by n, or we can write r equals to n times a, this is sine alpha divided by alpha. Okay, r equals to n a sine alpha divided by alpha. This a is amplitude of individual source, and this n is the number of sources that you have considered. So n times a gives you the overall amplitude through that slit. Okay, amplitude of the total amplitude through the slit, n times a. So we will now analyze this r equals to n a sine alpha by alpha, or else we can take any other value for this n a. So I will write r equals to some, let's say small r sine alpha divided by alpha. So this is the resultant amplitude. This r equals to n times a. N is the number of secondary sources that you have considered. Capital A is the amplitude of individual secondary source. So it is in the form of r equals to r sine alpha by alpha. So I will find out when the intensity will be maximum, minimum, what are the other condition, if there is any possibility of secondary maximum or something like that. So we know I is proportional to r square. I is proportional to r square of the amplitude. Using this, I will be able to find out the intensity. So in the next video, I will show you how to find out the maximum condition for maxima, principal maxima, secondary maxima, and the minimum for a single slit diffraction. Thank you.